Hello everybody and welcome to lesson 1 on stoichiometry. Today is going to be a very tough day, but what I can tell you is that it is probably the most important lesson that we're going to do in the entire course. We're going to be talking all about stoichiometry. It's a fun word to say, not a very fun set of topics that we're going to cover. Stoichiometry is basically divided into two different categories. Category number 1 is composition stoichiometry, and that pretty much takes care of what we talked about last unit, or last lesson rather, with our conversions of moles, and we can either go from moles to grams or mass, or moles to molecules or atoms. And these are very important conversions that you will see over and over again. And you'll even see them in reaction stoichiometry, which is our second category of stoichiometry. So reaction stoichiometry has to do with the conversion of moles of reactant into moles of product. And basically what that is quantifying chemical reactions. And so while stoichiometry is one of the most fundamental topics in chemistry, it's also one of the most challenging. And it is one of those topics that comes back in every single unit throughout your entire first year of chemistry. So let's get right into today's content. First things first, we're going to talk about stoichiometry terminology. And what I would recommend that you do is, before just writing down all of this, pause and read each of these definitions on your own time and write each of these definitions in your own words. And then I will talk about sort of my thinking with each of these terms. So a mole can be thought of as a packet of atoms or molecules. So that's what we talked about last lesson, where we were talking about maybe a carbon atom. And then we wanted to scale up. Let's just draw this as one little fundamental unit. And we scale up into a package of a ton of these carbon atoms. And it's this many carbon atoms, times 6.022 times 10 to the 23rd, which is Avogadro's number. And so the idea is a mole is simply a bunch. And the reason for that, as we talked about last week, is that this is measured as 12 atomic mass units, whereas 1 mole of carbon is measured as 12 grams per mole. And that's super, super important, because in the lab we measure things as grams. We don't measure things as atomic mass units. And that is the very purpose of the mole. Molar mass is the weight in grams of 1 mole. And so what I want to point out about these 2 points is that when it comes to the stoichiometry that we're doing today, everything is going to be in moles. And what that means is, when you're running a chemical reaction, you're talking about putting in 12 grams of carbon or 1 mole of carbon. You're not talking about, I'm going to run this reaction with 1 carbon atom. It just doesn't work that way. It's way too difficult on our macro level of the universe to run reactions that way. So everything that we talk about from here throughout the rest of today will be in moles. So some specific terminology with reaction stoichiometry involves the limiting reagent and the excess reagent. So if you're running a chemical reaction, you are always going to have one thing that runs out and then one thing that has some amount remaining if they're not in perfect ratios. So the limiting reagent is going to be the reactant in a chemical reaction that runs out first. And what that means is it's going to limit the number of reactions that you can run. And then the excess reagent is simply the other thing. So the thing that has enough and can keep running reactions, except your limiting reagent runs out, so you have leftover excess. If that doesn't make any sense just yet, don't worry, because we're going to talk about all that in a lot of detail today. So the first thing that I want to do is talk about the chemical reaction on its own. And so we're going to look at this reaction. It is a combustion reaction. We're going to see a ton of combustion reactions throughout the course of this unit. And basically what this reaction is saying is that you have some input. And so you're putting these two materials, in this case it is ethanol, C2H5OH, and oxygen, O2. You're putting them together and they are reacting, and then the output is going to be what you see on the right side of the equation. So on the left side is your input, or in other words, your reactants. And then on the other side is your output, or your products. And one thing that you'll notice is that each of these chemical species has a coefficient in front of it except for ethanol. And what that coefficient means is basically it takes 3 moles of oxygen to run one of these balanced chemical reactions. And I like to write out units for each of these coefficients. And what this 3 means, for example, is that it takes 3 moles of oxygen to run one chemical reaction. And you're going to see this a lot today. This RxN just is an abbreviation for reactions. So for our carbon dioxide right here, CO2, what that means is you get out 2 moles of carbon dioxide per reaction. And with the water, 3 moles of H2O per reaction. So what does it mean when a chemical species doesn't have a coefficient at all? What that means is that the coefficient isn't 0, it's 1. And so when you don't have anything in front of the C2H5OH, what that really means is that it's going to take 1 mole of C2H5OH to run one chemical reaction. And so this is all really, really important for how we're going to approach these stoichiometry problems. Because what this chemical reaction is saying is that it takes 3 moles of oxygen for each 1 mole of ethanol. And when you react in that ratio, your exact output should be 2 moles of carbon dioxide and 3 moles of water. So before we get into quantifying these chemical reactions, I want to put stoichiometry in perspective. And this is something that you'll see very commonly is professors and YouTube videos out there are going to try to put stoichiometry into common terms. And so I'm going to do just the same thing. So how I define stoichiometry is that it is simply the recipe for a chemical reaction. And hopefully at some point in all of our lives, we've done some sort of cooking to know that it takes certain ratios to come up with certain food items. So our recipe for one sandwich in this example is going to be 2 slices of bread, 1 slice of turkey, and 3 pickles. And the question is, how many sandwiches can you make with what you have in the kitchen? And what you have in the kitchen is 12 slices of bread, 6 slices of turkey, and 6 pickles. So I'm going to actually take you through this mathematically and how to use the units to come up with the answer. So if I have 12 slices of bread and it takes me 2 slices of bread per sandwich, I want to cancel out the units of bread. And I know this is a little silly. And I'm going to get 1 sandwich. So I'm just doing the same types of dimensional analysis that I did last week, right? Because I'm canceling out bread and I'm ending up with the units of 6 sandwiches. So for turkey, I can do the exact same thing. So 6 turkey. And then for every sandwich, it's going to take 6 turkey. Sorry, it's going to take 1 turkey per sandwich. And that's going to be 6 sandwiches once again. So we have perfect ratios of turkey and bread. However, when it comes to the pickles, I have 6 pickles as well. But every sandwich is going to require 3 pickles for every sandwich recipe. I'm trying to scrunch that in right there. And I'm going to end up with the ability to make 2 sandwiches. And so what you're going to see here is that if I tried to make a 3rd sandwich, I wouldn't have the right amount of pickles to run my recipe. And therefore, the number of pickles that I have limits the number of sandwiches. And so my answer for how many sandwiches I can make is simply 2. And what that means is if you wanted to take inventory or you wanted to know how much you have left over, you do have excess bread and turkey. And what we're going to do in reaction stoichiometry is exactly this calculation, except instead of pickles, maybe I'll do 6 moles of oxygen, and then it takes 3 moles of oxygen to run, and instead of sandwich, I'm going to talk about 1 chemical reaction. And that's going to get me the ability to run 2 reactions. And we'll see this in examples throughout today. But the math is the exact same thing. The only thing I'm doing is I'm taking it out of the kitchen and into the lab. We're still running a recipe. We're still using these ratios. We're just using these more complicated chemicals than bread, turkey, and pickles. So keep that with you. Try to allow this to give you some confidence in your understanding of the more difficult topics. And we're going to move straight ahead to chemical reactions. So first, I want to work on a generic reaction. And what that means is that there's no chemicals here. It's simply variables that would represent a chemical reaction. So we're going to assume that this is balanced. And what I'm doing is I'm putting in 10 moles of A and 10 moles of B. So I'm going to write these up here. So 10 moles of A and then 10 moles of B. And we're going to see if we can come up with a calculation almost exactly like we did with the sandwiches and come up with an answer for how much C product we can form. So let's take a look at this. I'm going to start with A. And my question here is how many of these balanced chemical reactions can I run? So I have 10 moles of A. And every balanced chemical reaction, I'm going to use the coefficient here. I need 1 mole of A to run 1 chemical reaction. And therefore, with 10 moles, I can run 10 reactions. For B, I have 10 moles of B. But in this case, every reaction is going to take 2 moles of B. So I'm going to write here 2 moles of B per reaction is equal to 5 reactions. The limiting reagent, by definition, is the reactant that will run out first. And mathematically, in this case, it is the reactant that will allow you to run the fewest number of reactions. Therefore, B is 100% my limiting reagent. I'm going to abbreviate it to look like this. And A is my reagent in excess. So let me show you how to finish this problem. Now that we know that we can run 5 reactions, I can use that value if I wanted to figure out how much C I'm forming. I use that 5 reactions, and then I say for every reaction that I run, I get out 3 moles of C. And that gets me with a final answer of 15 moles of C formed in this chemical reaction. And that is the final answer. So moving right along here, now we're going to work on some real chemical reactions. And this reaction is the oxidation of iron. So it is iron, Fe, and I'm just going to write that out, that this is iron. We're adding oxygen and we're forming what we would call iron 3 oxide. We'll worry about those names and nomenclature a little bit later. But I'm dividing this into several different question types, ranging from the easy question all the way into the difficult question, which is the limiting reagent question. But what I want to show first and foremost is that the first step with any limiting reagent or any basic stoichiometry problem is that you need to balance the chemical reaction first. And usually a question will tell you that the reaction is unbalanced or that it is balanced. In this case, it is unbalanced, and you are expected to balance the reaction before trying to do any stoichiometry. So I'm going to balance it, and if I'm looking at this, there are multiple ways of going about this. I like to balance the oxygen first because the oxygen has a 2 here and a 3 here. And so I know I can add a 3 here and a 2 here. And so I have 6 oxygens on both sides. And then I can balance the iron by putting a 4 here. But overall, in the beginning, balancing chemical reactions is just going to be a guess and check. You just need to make sure that you have the same amount of each element on each side of the equation. So the easy questions, why do I call them easy questions? Well, the answer is each of these is a perfect ratio to the balanced chemical reaction. And what I mean by that is if I wanted to really break this down, I would say I have 4 moles of iron and it takes me 4 moles of iron per reaction. And so I can run 1 chemical reaction. And with oxygen, it's the same thing. I have 3 moles of oxygen and it takes 3 moles to run a single reaction. And that gets me 1 reaction. And so there is no limiting reagent. You're just adding things in the perfect ratio, which is really nice, and it makes the math almost unnecessary. So in this, what we just determined is that we can run 1 reaction, and every reaction is going to get me 2 moles of the iron 3 oxide. Therefore, the answer here is simply 2 moles of Fe2O3. So in problem number 2, all we're doing is we're doubling the amount that we started with. And so it should be intuitive here that you run 2 reactions. And so if I double the amount of reactions that I'm running, I'm doubling the amount of product that I can get. So this is going to be 4 moles of Fe2O3. Now, question number 3 is a little bit more difficult because now I am actually adding in half of the amount that I had in question 1. And so what I'm doing is I'm actually running 0.5 reactions. And so what does that mean? That means I'm expecting half the output of 1 single balanced chemical reaction, which is 1 mole of Fe2O3. Now, these are just conceptual questions. These are questions that I'm asking to make a point about balanced chemical reactions. On homework, on a quiz, or on a test, you should always absolutely work out the entire problem and not just jump to conclusions. So let's take a look at this difficult question now. Beginning with 10 moles of iron and 5 moles of oxygen, identify the limiting reagent and the number of moles of your iron 3 oxide product. So this would look just like what you saw in the video, and we're going to work it out. So let me zoom out so we can see everything. And I want to show you each and every step of a stoichiometry problem. So step number 1 is going to be to balance. Always, step number 1 is going to be to balance. Step number 2 is find the limiting reagent. I'm going to abbreviate that LR. And we did this in the previous problem. So let's take a look at how you do this. I'm going to take a look at iron, and I have 10 moles of iron, and every reaction requires 4 moles of iron to run 1 reaction. And if you're wondering why I'm doing this, take a look at the units and notice how they cancel out and leave me with just reactions. That's going to be 2.5 reactions. And the reason I'm doing that is because these values up here are set in stone, but I can put any number I want into the reaction system. And so they're always going to react in a particular ratio, and that's going to get me a particular number of possible reactions. For oxygen, I have 5 moles of oxygen that I'm putting into my reaction, but every reaction requires 3 moles of oxygen to run a single reaction. And so what that's going to get me is 5 over 3 reactions, or about 1.6 continuing. I'm just going to write 1.67 reactions. And so take a moment here and ask yourself, what is the limiting reagent based on the calculations that we did? And hopefully you are just internally screaming, it's got to be oxygen, because you can run the fewer number of reactions and therefore it's going to run out first. I'm going to write, this is the limiting reagent. And what that means is with the amounts of both iron and oxygen present, you can only run 1.67 reactions. And so that's how we're going to finish this problem. Step number 3, find the moles of product. And the way I'm going to do that is I'm going to take that 1.67 reactions, and then I'm going to multiply it by the coefficient of my product. So for every reaction, the amount of iron 3 oxide that I form is 2 moles Fe2O3. And what that's going to get me is a final answer of about 3.3, and this would actually be 3.33 continuing moles of Fe2O3, assuming that I don't round that all the way. And so that's our answer. And I understand that is an ugly 3. Let me fix that. There we go. So the last problem that I want to work in this particular section, and we'll continue with some difficult problems in part 2, is this question. So this question is asking, what is the maximum mass of carbon dioxide that can be formed in the combustion of 3 moles propane? Propane, by the way, is this right here, in the presence of excess oxygen. And so I want to show you a bit of an advanced stoichiometry technique on this question, because you get to a certain point where you don't necessarily have to do all the calculations that we did in the previous problem. And the reason why is because they're actually telling me what the limiting reagent is, because if oxygen is in excess, that means that we put enough oxygen here into this reaction system to make sure that the propane is the limiting reagent. And so we know that propane is the limiting reagent. And so what I'm going to do is say that I have 3 moles of propane, And for every mole of propane that reacts, so every 1 mole, because the coefficient on this is 1, I'm going to get an output of 3 moles of carbon dioxide, and that's going to get an answer of 9 moles of carbon dioxide. However, I want you to ask yourself, is that the final answer? And look at what the question is asking you. What is the maximum mass of carbon dioxide? And so we get to use one of our techniques from last lesson so that we can convert the number of moles into mass. And the way we do that is if we have 9 moles carbon dioxide, we can multiply by the molar mass to get simply the mass. How do we get the molar mass of carbon? Let's do a quick recap from last unit. We have carbon. Let's just take it up here. We have 1 carbon, so 1 times 12, plus 2 oxygen, and that is 2 times 16. I'm getting these values from the periodic table, and that's going to get me an answer of about 44 grams per mole. And so if I work out this last part of the problem down here, I have 9 moles of carbon dioxide, and then I multiply by the molecular weight, which is 44 grams per mole. Check out how these units cancel out. And that's going to get me an answer. I actually haven't calculated this out. 44 times 9, which is about 396 grams. And that is your final answer for this problem. Notice that what we did is all around here, we did some reaction stoichiometry. And then this last step here was composition stoichiometry. So before we transition to part 2 of this lesson, I really recommend that you look at these questions that are coming up and try to work them out on your own. Take a minute before continuing to the next video. Try your best to work out these questions. I believe there are 2 remaining, and see where you get stuck so that when you watch the video, you have questions that hopefully will get answered. So good luck with that, and I'll see you at part 2.